welcome to part 2 of 2.1, study of motion. So, what do we already know? We know the definition of velocity and the definition of acceleration come from our distance versus time and velocity versus time graphs. We have two equations for them. They won't show up in your data booklet, but they are important to know. And then we have this equation for how to find the distance from a velocity versus time graph. If you know the initial velocity and the final velocity and it changes over time, you can get a distance using this equation on the right. So the other type of graph you could, of course, do is an acceleration versus time graph, but they're always going to look kind of the same. They're always going to be flat. This is because we're talking about uniform acceleration in IB physics, no changes in acceleration. But they are different, and they're important to know the differences. A is a zero acceleration graph, which means that there's going to be no change in your velocity or a constant velocity, straight line. B is going to be a positive acceleration, or your velocity is going to get bigger. If it's a positive velocity, it gets more positive. If it's negative, it gets more negative. C is a negative acceleration, so it's going to be working against your velocity to decrease velocity and get smaller and smaller over time. In an acceleration versus time graph, the area under the curve for a specific amount of time is going to give you an increase in velocity from wherever you start to your final velocity, given by this equation down here. And so now that we know those three equations plus that one I just showed you, we could combine some of those to create some more useful equations that are going to help us when we do our problems. So for example, if you don't know the time, this combination of the equations gives you velocity squared is equal to your initial velocity squared plus 2a times s. If you don't know the time, but you know three of the other things, you can definitely figure this out. And then the other equation is super useful, and you'll see why in a second. If you know acceleration and where you start, all the starting information, and you want to figure out where you end up in distance. So these are our new equations just by combining some of the old ones. If you want to see how you get these by combining them, I could show you sometime if you're curious. So let's do a check-in with these new equations. A car has an initial velocity of u, which is 5. After a displacement of 20 meters, its velocity is now 7. And they want the acceleration of the car. Note you weren't given time, which is when this equation right here is super useful. So go ahead and try it. You should get an answer of 0.6 meters per second squared. Let me know if you need me to show you how to do it. The second question, a car accelerates from rest to 28 meters per second in 9 seconds. Now they told you nothing about the acceleration of the value of it. They want distance, you know final velocity, you know time, and you think you know initial velocity, maybe? It depends on how good you are at English. The word rest means that you didn't have an initial velocity or it's 0 meters per second. So this is when you're going to need to use this equation. You can't use this one. Don't try and use it. You need the 2 because you don't know if it was a constant velocity the whole time, which is what this equation implies. So use this equation to solve for it. And I'm trying to remember what answer you get there. I think you get quite a large distance because you're taking all of that information. Why don't I just do it? 126 meters if you take 14 times 9. So that is how you do check-in number 5. Again, if you didn't do them yourself, you really should work them out yourself. And so let's summarize those motion graphs together. There's a special relationship between them in terms of gradients and areas. If you have a distance versus time graph, the gradient will give you a velocity over time. If you have a velocity over time graph, you're going to get an acceleration over time graph if you do the gradient. And the opposite works for area. So if you know the acceleration over time, you're going to get the area becomes velocity. If you have velocity over time, the area will give you a distance over time. So these 5 equations will show up in your data booklet, and you can use them on the test. You don't have to memorize what they are, but you do need to memorize what V and A and U and S and T are. So now to part 2 in real time. Accelerations are great and we're used to them when we accelerate our car. But the one acceleration you're probably really used to and you didn't know scientists actually have a lot of info about is what we call free fall. When something is falling under the influence of gravity only. Nothing is pushing it up, nothing is pushing it down, just gravity. And so scientists have measured this over the year, and there is an exact acceleration that happens because of gravity. It is 9.8 meters per second squared. And so the same equations we just figured out can be used using this acceleration due to gravity when you have vertical problems. So let's try it. So we have a stone which is thrown up from the edge of a cliff, which is 35 meters up, and its initial velocity is 8. And so they didn't really give us a lot, but if you think about it, we know that stones are under the influence of gravity only, so we know its acceleration is 9.8. So we have A, we know its initial velocity is 8, so we have U. And we do have a distance, but we'll see if that's useful depending on what we're looking for. So A asks for the height that the stone can go upward. So that initial distance won't be useful for A, but we do need to know some more information in order to use any of our equations. We want a change in velocity from 8 to 0 because we want the stone to stop as it goes upward. And we want to know how high it goes. So we want an S. So we want an S. We know of an initial V or a U, and we know an acceleration. So you're actually going to want to use this equation to figure out how high it goes. And you need to know by personal experience that when you throw something up, it stops at a height, so it has a final velocity of 0. So this will be 0 equals 8 squared plus 2 times 9.8 times S, and you just got to solve for S. So you can figure out exactly how high up it goes. It's not too hard. You just gotta, figure it out. You should get a height of about 3.26 meters. And so that's how high up it starts, above the 35-meter cliff. And so now you can use that combined distance for how far it's going to fall and figure out the time it takes to hit the sea. So again, it's starting with no speed as it falls downward. And you're going to figure out your t, so this goes away. And you're going to just have that 35 plus 3.26 is going to be 1/2 AT squared, where A is 9.8. So you're going to go ahead and solve there. And don't forget to do a square root to find the actual time, not just the, time squared. And so you should see that it takes about 2.8 seconds to get to the ground. The velocity just before it hits the sea is going to be obviously using one of these equations. We know time, we know total distance, we know the initial velocity is 0, so this equation I'm hovering over will be the easiest. So we take that time and we're going to need to figure out, so it goes a total distance of 38.26 multiplied by 2 divided by that time we just got. You should find it somewhere in the 5-ish meters per second is its final velocity. And so the total distance it covers, remember, distance is not a vector. It doesn't care which direction you're going. So we need to add up all the distances. So the distance up, then the distance back down to the top of the cliff, plus the 35. So in total about 41-ish, 42-ish meters, depending on where you're rounding. And then, of course, the average speed and the average velocity, which will be different because average speed is your distance over time, average velocity is your displacement over time, and the total displacement is 35 meters versus the total distance is about 42 meters. So you're going to get different numbers for both of those. So the other thing that happens when you have accelerations is sometimes your changes in speed are in different directions. So when you have a motion happening in 2 directions at the same time, you need to factor in all of the things. So let's talk about this problem where a man wants to cross a riverboat using his motor, and he wants to go at 4 meters per second straight, but the river, which is 30 meters wide, which is how far he needs to go across, is pushing him to the side all the time at 3 meters per second. So you're going to just handle the 2 directions separately and figure out what's going on. So if he could go forward at 4 meters per second and he needs to go 30 meters, you just need to use the distance and the velocity to figure out how long it's going to take him. And so we have a super easy equation for that. If it's a constant velocity, you know, delta S over delta T is V. So you just take the 4 and the distance of 30, and you figure out that it takes him about 7.5 seconds. And so during that time, he's also getting pushed to the side. And so question A wants you to figure out how far to the side is he going to be in distance. So if he's getting pushed at 3 meters per second for 7.5 seconds, you figure out that he ends up about 22.5 meters downriver. And so most people actually autocorrect for this while they're moving, but some people just drift. And so that is kind of how you handle it in two directions. And I'm going to just leave it there, right? That you have to deal with both of them. And we're actually going to come back to this after you do just some basic problems with the rest of the equations, because it starts getting complicated when you have two directions. So hopefully this helps.